तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been discussing the metal semiconductor contacts. We started the whole thing because it was necessary for MESFET in gallium arsenide FETs. Now, we have spent about a couple of hours on this. We continue on this because few things have to be sorted out, okay, which are very important for making rectifying contacts and also ohmic contacts particular. This is a diagram which is redrawn just showing only the conduction band, okay, just showing only the conduction band. For example, here you have got 3 curves which are the conduction band represented for thermal equilibrium, T referring to thermal equilibrium and RB referring to reverse bias, FB referring to forward bias. So, you can see that on the left hand side of this, which represents the metal, I have also given the density or distribution of electrons above the Fermi level. So, on the right hand side, with reference to the conduction band, how the electron distribution is there at thermal equilibrium is put here, and the dotted line on the top tells you that the electrons on both sides are going up to a particular level. There is no net current flow. We have discussed it more than once, but just put it in a different way, just only showing the conduction band, because after all now the interaction is, if it is n type semiconductor, the interaction is between the electrons and electrons. Okay. If it is p type semiconductor, we need not look into conduction band at all. We look into the valence band, because the interaction is between the holes and holes, plus charges and plus charges, or absence of electrons and absence of electrons. That is more correct term, because in metal people do not talk of holes as it is, but you can talk of absence of electrons, levels which are not occupied. So, that is actually finally what matters. So, here, so you can see that in thermal equilibrium situation, you have got the electrons transferred. We are talking of a case where phi m is greater than phi f s. Okay. Now, just going quickly through that, the electrons have got transferred from the semiconductor to the metal, leaving plus charge on this side, minus charge on that side. That is the built-in potential. In fact, from this end right up to this barrier tip, that is the built-in potential. Now, you can see the next diagram. Okay. In the forward bias condition, if you see, the polarity of this voltage is opposing the built-in potential. That means the total potential now what was here is reduced, because that is lifted up now by an amount equal to the applied voltage. Now, the carriers also have the distribution with respect to that, the whole this curve, what is brown has become blue now. Okay. So, that is having few electrons which have energies greater than the energies of the electron in the metal. So, that is the one which gives rise to transport of electrons from the semiconductor to the metal, which gives rise to a current from metal to semiconductor, and okay, that is what is marked here. Metal to semiconductor, there is current flow. Okay. Current flow is from metal to semiconductor due to transport of electrons, these electrons, extra electrons. Now, when you reverse bias, the entire potential is plus here, same polarity as the built-in potential. So, if that were the built-in potential there between this point and that point, it has gone up now by amount V r. This is extra voltage that you applied additional to the built-in potential. So, the electron distribution now tip is at a much lower energy than that. So, these electrons are not able to climb up the barrier. So, the current is only due to these electrons which are there from left to right or from the metal to the semiconductor, which I have okay. I just going through that in a slightly different way, but only looking into conduction band. That is the one which gives rise to the I naught. Okay. The transport of electrons from here to here, which actually implies the current from semiconductor to the metal, reverse bias current. So, we also have seen, we will in fact derive this and show later that the IV characteristics of this device is given by the same equation as that of diode, only the I naught is different compared to p-n junction. The mechanism of I naught is different, that we will see when we discuss the IV characteristics next in a couple of lectures. Now, reverse bias P put equal to minus VR, that term goes off, you get minus I naught, telling you that the polarity is reversed there. Okay. So, this is summing up the whole thing, that same equations what you have written, but what we again reiterate is low I naught will give a good rectifying contact, high I naught will give a poor rectifying contact or a good ohmic contact or closer to ohmic contact, and that again, as we were telling, depends upon this height. Okay. This height, if it is lower, more of these charges will be able to cross, I naught will be larger. This height is larger, then the electrons which are above that barrier are less. So, less current, I naught is less. So, for a good rectifying contact, phi b n should be larger. This is the p-type semiconductor, which I just started discussing yesterday. Now, we do not put the entire energy band diagram. You can see what we were showing for the conduction band like that is now shown for the valence band. So, this will be the valence band. Okay. Just if I go to the board, I will just show you that diagram once, then you can see it. So, p-type semiconductor. What we said is we are talking of a situation where phi m is less than phi of s. That means electron transfer from the metal to the semiconductor. So, what happens ultimately is you get a curve like that. A p-type semiconductor, electrons have got transferred from here to here, this has got negatively charged, field is in that direction, so energy band diagram is like that. Okay, this is the thermal equilibrium situation. How much is this bending depends upon the difference between phi m and phi of s. The phi m and phi s difference is the difference between the two Fermi levels. They equalize, there is a built-in potential coming up, which is equal to difference between the Fermi levels. Okay. It is same as the p-n junction, difference between the p-type material and n-type Fermi level, that is the built-in potential. Solve what you have to keep track of the Fermi level differences. So, phi m minus phi f s or phi s minus phi f m. So, that diagram what I have drawn there, the board, the bottom, here what we are drawing is only this portion, that portion, okay, and I have stopped here, thermal equilibrium situation. So, that is the diagram which we have shown in this slide. Okay. So, if you look into the slide here, okay, now the brown curve again is the thermal equilibrium curve, that one. Okay. Now, the polarity of this built-in potential is plus here minus here, because phi m was less than phi of s, the Fermi level in the metal was at higher level, the difference is less compared to that. So, the Fermi level in the metal was at a higher level. So, electrons have got transferred from the metal to the semiconductor, you have got plus minus voltage there, built-in potential, exactly opposite to that of metal n layer. So, reverse. So, this is the VBI, that VBI is exactly similar to that you can say, and here this portion is the phi BB. If you go back here, this is the phi BB, okay, that is the phi BB, and this is actually phi BN. sum of the two is equal to Eg, band gap. So, in all the cases the sum of phi Bp plus phi Bn is equal to Eg, band gap. Band gap is this one. Okay. So, that is the situation in this particular case. What I have shown is the phi Bp here, then this thermal equilibrium by this curve, and this distribution is the distribution of holes. Just like you have holes in the conduction band up to certain level going up, electrons in the conduction band above the conduction band, that distribution, same distribution, similar distribution is there for the holes in the valence band. I can talk of absence of electrons similarly in the case of metal here, though I do not like to talk of, or people do not appreciate if you say holes in metals, what holes are there? There are not real holes there, okay? There are absence of electrons. So, vacancies are there, because after all the electrons, if they are moved from metal to the above the Fermi level, there are vacancies left here, and more number of vacancies here. Please notice, for the vacancy the lower energy is up, higher energy is down. So, the vacancies tend to occupy the higher energy there, more of the vacancies are there, less of them here, okay? Because electrons tend to occupy lower levels. So, the vacancies are left at the top. Okay. So, that is why here also you see, you can see the distribution of holes is more here, less as you go down in energy. Now, you can see these tips are matched to one another here at thermal equilibrium. Now, if I reverse bias, the polarity of the reverse bias means actually, what do you mean by reverse biasing? I am increasing the barrier. So, the barrier here is from this point right up to this point, that is the barrier, okay? Phi Bp minus difference between the valence band and the Fermi level. In the case of phi Bn, n-type material, the built-in potential is phi Bn minus Ec minus Ef. Here phi Bp minus Ef minus Ev, similar thing just, okay. So, I do not have to reiterate that. So, now here this polarity of this voltage, if it is the same thing, what was like this here, the band bending there will increase, it will push the band energy band diagram valence band upward. So, that is the reverse bias situation, that is whatever built-in potential was there, you add up this quantity, that is extra voltage that you are adding up, okay. That extra voltage added up is Vr, and you get reverse bias. There is a small problem here. I have just shown the depletion layer here, okay. This depletion layer actually should be wider. In fact, I just copied from there. Here you see thermal equilibrium, forward bias depletion layer decreases, reverse bias increases. So, actually here it should be the same way. The reverse bias, the depletion layer should increase. So, this should have been there. We have to correct it, okay. So, the depletion layer is D is for depletion layer, it will be wider in the reverse bias case, and in the forward bias case the depletion layer will be narrower. So, when the depletion layer is wider, the barrier height is more. When you forward bias here, the polarity of this voltage is opposite to that. That means the potential you are reducing, that means the depletion layer will actually here will be smaller, okay. Once the depletion layer here is smaller, barrier height will be smaller. So, now you can see, when you reverse bias, the tip of this whole distribution is below that level barrier, none of them can cross the barrier. The current is only due to these holes which are above this crossing from this end to that end. That means current will be only due to the holes which are crossing this end to that end, that is I naught. So, whatever left out current from the carrier transport from the metal to semiconductor, whether it is holes or electrons, as the case may be n type or p type, that gives rise to I naught. Now, when you forward bias, this is pulled down here. So, you have more of these holes which can cross from here to here compared to this. So, you have the whole current from, when you forward bias, you have got whole current from here to here, semiconductor to metal. equation is same thing. So, in fact, I think you should be now, we had so much detailed discussion on n type and I gave a glimpse of the p type, you can actually sit down and work it out in detail. Idea is that one thing you remember, reverse bias depletion layer widens, forward bias depletion layer narrows, okay. That part you remember. Reverse bias barrier height increases on the semiconductor, forward bias the barrier height falls. Okay. So, the current transport is there in the forward bias case. In the n type semiconductor, the current transport is transport of electrons from semiconductor to the metal. In the case of p type material, forward bias barrier is reduced, current transport is due to the transport of holes from the p type to the metal. So, current directions are different. Current in the case of metal n type semiconductor, in the forward bias cases current is from metal to semiconductor, just like p n junction, p to n. In the case of p type semiconductor, current is from p to metal, that like a p n junction. Okay. These are the things to remember. Equation is the same, I naught into e to power v by v t minus 1, forward bias case. Reverse bias is I naught. Okay. So, with those things, what we now see is, so this is what I have said already, that phi b p is phi b p plus phi b n is E g, and in this case also whether it is rectifying or ohmic in this case also depends upon the barrier height. If phi b p is small, I naught is large, it is closer to ohmic contact. Phi b p is large, closer to rectifying contact. So, in summary about these all types of rectifying contacts, phi b n what we have derived or we have seen is phi m minus chi, that we have said right at the first order theory. Phi b p is actually equal to, because sum of phi b n phi b p must be equal to E g. So, phi b p is E g minus phi m minus chi. So, what our thinking is, once your phi m is fixed, phi b n is fixed and phi b p is fixed. Okay. So, that would tell us phi b n should be large for rectifying contact, okay, in the n type material. That is straight away tells us, that means phi m minus chi should be larger. If phi m minus chi is high, if phi m minus chi is high, E g minus that is low, that is phi b p is low, that is ohmic. So, if phi m minus chi is large, that is rectifying n type, p type is ohmic, reverse is true in other case. So, people have generally say phi m is larger than phi s, you get rectifying in n type and ohmic in p type, and other condition is exactly opposite. Now, the hard reality is all these are idealistic theories. When you make the device, there are several other problems which come up. Okay. Measurement of phi b n, that is the ultimate truth. Is it phi m minus chi? If it is phi m minus chi, phi b n must be dependent on phi m. That is, if I choose different metals, I must get different phi m, that will be there. If I choose different metals, therefore, I must get different phi b n. Okay. It is not satisfactory. Experiment, see that curve there. These are the real measured values. I am really wonder the amount of time and effort that has been put forward for these measurements. Here you see only 4 points, but the amount of time that must have been spent for this is enormous. This is reported in literature way back. On the x axis you have phi m, made Schottky barriers on n type substrate, silicon, I am just quoting silicon straight away, and then the phi b n actually in that case, what you should have expected is phi m minus chi. If it is 4.2, the phi b n that you must have got would have been, for silicon chi is 4.05. So, what you should have got would have been 0.15. Now, you see here there are two values for that aluminum, one is black, one is that here, 0.75 electron volts the cross says, and for the same material the black dot says it is 0.5, both of them away from your theory. So, it shatters your theory totally. Okay. Now, take this black cross curves, Now, before you keep wondering what is this cross? Cross is made on a surface which is freshly cleaved. You cleave silicon, you get all those dangling bonds hungry for grabbing electrons, okay, surface states. That if you make a metal semiconductor contact, you get a barrier height which is practically independent of phi m. Where does our theory stand now? Okay. Phi m minus chi, pi m we varied from 4.2 right up to 4.8. The barrier height was about 0.8, 0.8, 0.8, 0.8. So, this is where we have to work out. This is where the difficulty is making OB contact and rectifying contact. You have problem because of this. Now, that is freshly cleaved surface. You prepare a metal semiconductor contact slightly differently on the same substrate. Instead of cleaving, what you do is chemically prepare. Clean the surface chemically, HNO3, HF, clean up you give. Now, the barrier height is lower, but getting closer to the what you think it is. You think it is phi m minus chi 0.15, but it is still about 0.5. And you also see that there is a variation with phi m. So, what you say is partly true. So, if you take a look at this curve, you will feel okay, I am a bit closer to the theory. If you take a look at this curve, you will be heartbroken, okay, because totally new theory you have to work out. But we do not have to work out that new theory, we have to see what we have neglected. Let us see other curve. So, I hope this portion is clear enough. Freshly cleaved surface, lot of dangling bonds are there. Chemically treated surface, there will be some sort of layer will be there which satisfies some of those dangling bonds, and when it satisfies, it gets closer to the ideal surface. In the theory that we have derived, what we said is a good surface, metal is in very good contact with semiconductor, no surface states, no interface states, then phi minus chi. So, you reduce, if you have the high interface state density, that is very high. If I have reduced the interface state density, then behaves some sort of behavior that we have seen, but not exactly the same value. This is on gallium arsenide. See, I just put that down first for silicon, it is remarkably seen there. Gallium arsenide on 110 oriented gallium arsenide, cleaved surface, it is not all that flat, but it is still, again you see phi m is 4 or some 4.2 or so, you get again about 0.8, something like that. Okay. And if you take gold, see these are the curves, indium, tin, copper, silver, gold. I think one more curve is there, copper and silver here, gold is that point. These things which are put here refer to those points. These are going up like that, similarly these are going up there, that is the indication. Okay. Instead of putting on the x axis, it has been put like that. It is taken from literature straight away. Okay. So, straight away copied onto without so I did not want any change from what is reported in the literature. So, now here you see this is also too far from the theory. There is slight variation. You take a look at chemically prepared, slightly better variation in the same indium, you can see it is about 0.6, which was showing earlier close to 0.8, has shown now 0.6. So, there must be some method in all these things. There is some law which follows this. In fact, if you examine the law, what follows is that. How it comes up, we will see today very shortly. So, for example, we said phi b n is equal to phi m minus chi, but it is much more complicated than that. Okay. It is an equation well accepted, way back it has been derived, but if you include the effects of the surface states, you get this equation. If gamma is equal to 1, if gamma is equal to 1, see that is phi b n equal to gamma. What is gamma? We will see afterwards. We will derive this equation. It is very simple, because if you know the theory, you can derive it in 4 steps. We will do that today. Gamma, if it is 1, phi b n becomes equal to phi m minus chi. That is our theory, the first order theory. Okay. In fact, that would correspond to interface state density 0, ideal. And if gamma is equal to 0, gamma equals 0, that is freshly equilibrium surface, gamma is 0. Okay. With ideal surface, gamma equal to 1. Freshly equilibrium surface, high density of interface states, gamma is equal to 0. So, if gamma equal to 0, that term is gone, and this is 1 minus gamma is 1. So, phi b n becomes equal to E g minus phi naught, and E g is fixed for a given semiconductor. That number phi naught, what it is we will see soon, that also is fixed. Once you fix a semiconductor, the E g phi naught is actually a particular level within the forbidden gap. That turns out to be for E g by 3 for gallium arsenide and silicon. For indium phosphide it is slightly different, it makes your life much more miserable for making MESFETs there, that we will see later on. Today we will focus on gallium arsenide and silicon, where this is E g by 3. Okay. Now, let us see what is the cause of this. Apparently or evidently, gamma is related to the interface state density DIT and some other terms. Gamma is between 0 and 1, it can be only between 0 and 1. Ideal 1 and worst 0. So, how that comes up, we will just see now. These are the. So, now let us take a look at to the little bit more of physics of this one. Effect of interface state on the DIT and phi b n, because we have seen here phi b n and gamma. So, here what we are seeing is the effect of interface state on phi b n through gamma. So, gamma is related to phi b n. So, what is said here now, I have summed up whatever is to be said. The surface is never ideal and has density of states, what you call it as density of states as DIT, that is the accepted symbol for interface state, whether you talk of MESFET, MOSFET or Schottky. Okay. DIT, and that tells you how many number of states are there per unit area of the surface within energy gap of 1 electron volt. So, if there are 10 to the power of 12 DIT per centimeter square per electron volt, if I take an energy gap of 0.1, 10 to the power of 12 per centimeter square per electron volt. If it is 0.1 electron volts, there are 1/10 of that. If I say DIT equals 10 to the power of 12, this is some number I am tossing out, per centimeter square per electron volt, then in an energy difference of 0.1 electron volts, you will have DIT equal to, total DIT will be, this is per centimeter square per electron volt into 0.1 will be equal to 10 to the power 11 per centimeter square. If it is not charged, you do not have to worry. If it is charged negatively, there will be 10 to the power of minus 11 into 1.6 into 10 to the power minus 19 Q. If it is charged positively, it is plus charge multiplied by Q. Q into DIT is a charge, and it can take one state, can take one charge only. Okay, so, due to the dangling bonds on surface, this interface state density is due to the dangling bonds on surface. That is one deviation from the ideality. Other deviation is, however much you struggle, there will always be a thin layer, a very thin layer, 5 angstroms, 10 angstroms. Okay. It could be a gap that is present when you put the metal, it could be a dielectric material which has resulted in due to the native oxide that is present. So, whatever you do, there will be thin layer, unless you forcefully try to remove, quickly put the metal. In vacuum itself you remove the oxide, vacuum itself put the metal, then there is chances that delta is 0. So, but otherwise you always will have a thin layer delta of the material, mostly native oxide, exists between metal and the semiconductor surface. SC standing for semiconductor. I just use the short form here, SC. Okay. Delta and the delta thickness of that layer and that DIT that we are talking of, interface density values, determine what is the value of gamma. So, if delta is 0, gamma effect is not there, you get phi m, okay. 0, okay, or DIT is 0, ideal condition, you get phi m minus phi. Let us go into some of those things. Now, this is the diagram which you must see, understand. Once you understand this, everything else is clear. This is an energy band diagram. In fact, you can see the difference between the size and the color that I put here, just to distinguish between them. There is no difference in size in the dangling bond. Dangling bond is dangling bond. Okay. So, what I put here is, there is one line here called E naught. This is the conduction band, the top. I just forgot to put that. There is conduction band there, but it is understood that when you put the energy band diagram, conduction band, valence band. So, what we have drawn is, this portion to the right is bulk region of semiconductor, and this on this line that I drawn is the surface of semiconductor. So, what we have done is, we have taken the semiconductor layer surface, then going into the bulk. So, on the surface also we are putting how will be the energy states levels will be. If you take the bulk, if there are no dopants, no imperfection, you do not see any levels. So, you will see only conduction band and valence band. I have deliberately suppressed all other levels. You may have dopants n type, then there will be a level which goes here. That we will discuss when we discuss actually the metal semiconductor contact. So, these each one of them represents the distribution. So, the surface states are represented by continuous distribution of energy levels. It is not separate, it is like a energy levels in a conduction band virtually. So, you have got one after another going. What is the reason? That we can just spend a couple of minutes on that. Why you call that dangling bond as a level which is distributed, levels which are distributed all over the band. 1. Why do you call there is a level here, all the levels above that you call them as acceptor states. So, same dangling bond behaves like an acceptor state, same dangling bond behaves like a donor state. It is not the same, it belongs to different atom. Okay. There are so many atoms, 10 to 15 atoms per centimeter square. Some of them behave like acceptors, some of them behave like donors. Okay. So, these levels below this are behaving like donors. Why we will see soon, but the moment you say the levels above this E naught are acceptors and the levels below that are donors, notice I have put here that level between E naught and EV is called phi naught. In the equation that you wrote, go back to that, there is a phi naught there. That phi naught is this one. This is the phi naught. The phi naught is the difference in energy between the level E naught, what is V naught we will see, E naught and the valence band, bandage. What is E naught? It is a level which separates between acceptors and donor levels. Okay. More precisely, suppose the Fermi level is matching with that E naught. If the Fermi level is coinciding with the E naught, what is the charge state of these donors? What is the charge state of acceptors? Please understand, all the levels below the Fermi level are occupied. Okay. Let me remove this now. Okay. Now, what we have done is, I am sorry, what I am trying to point out is, if there is a donor level, if the electron is occupying that is neutral. If the donor level is below the Fermi level, that level is occupied. If it is occupied, it is neutral. an acceptor level is a donor. An acceptor level you can represent like that. If the hole is removed from there, plus charge is removed, okay, it is ionized, minus charge. Here, if its electron is removed, it is ionized, it is plus charge. But otherwise, if the Fermi level is below this, if the Fermi level is below this, whatever level is there, it will be occupied. Okay. Now, let us see what happens is, if you take the donor level, you have to be very careful here. If the Fermi level is aligned with respect to that, okay, then the levels below that are occupied, they are neutral. The acceptor level are above that, the acceptor levels are not occupied. If the see, it is just the reverse. If the donor level electron is occupying, it is neutral. If the acceptor level, if the electron is not occupying, it is neutral. Okay. If it is not occupying, if the level is not occupied, it is neutral. If the level is occupying here, it is neutral. So, if the Fermi level, okay, is that clear enough? It is very simple to understand, electron occupying, not occupying. Okay. So, if it is occupying below this donor level, it is neutral. The acceptor level, if it is not occupied by electron, it is neutral. Okay. In the sense, this is neutral. If I remove that, it is occupying, negative. So, if it is occupying, it is negative. If it is not occupying, it is neutral. That is the understanding. So, it is simpler to visualize with the donors, because that is a physical thing. Electron not occupying, it is positively charged, electron occupying, it is neutral. So, you have the donor states can exist as neutral and Nd plus. This is 0 charge, occupied, not occupied, occupied, not occupied is that is removed, and acceptor state can be written as neutral, okay, and if it is occupied, minus. That is understanding. Okay. See, when it is ionized, what has happened at acceptor level? Electron has gone from the valence band and occupied that position. That is the meaning of that. But if the hole has pushed down to the valence band. See, when that is why you get Na0 and Na minus. Okay. Not occupied is plus charge, occupied is neutral. This is unoccupied, neutral, like that. You remove from there to there means what? Electron you have brought in there. You bring in one electron, that becomes negatively charged. That is why you occupy it, it becomes negatively charged. Unoccupied is neutral. So, with that understanding, you have to spend more time thinking about it. But simple thing to remember is, levels below the Fermi level are occupied, and if donor level is below the Fermi level, it is occupied, and when it is occupied, it is neutral. Acceptor level above the Fermi level is not occupied, okay, and when it is not occupied, it is neutral. That is simple thing. So, now, so this E naught is called the neutral level. That means, if the Fermi level is occupying into that, parallel to that level, okay, if the Fermi level is occupying the neutral level, what is the total charge at the surface? What is the total charge? I have interface state density uniform everywhere, DIT per centimeter square per electron volt. What is the charge? If the Fermi level is parallel, I am not saying it is occupying, if it is like this, what will be the charge? I would like to, okay, just again, you don't, there is nothing much to think. Supposing the Fermi level is occupying with the neutral level, that is E naught. If I draw a line there, that is the Fermi level. If I say, that means the very name tells you neutral level. If the Fermi level is occupying to the neutral level, charge in the surface is neutral, 0. Why? All these states below this neutral level are occupied, which are donors. Total charge there is 0 when it is occupied. Okay? And all these states above that are acceptors, they are not occupied. They are not occupied with electrons, that is neutral. So, when the Fermi level is aligning with respect, aligning with the E naught, charge in the entire surface is 0. You may have 10 to the power 15 charges per centimeter square, but charge will become equal to 0. So, the final thing that Fermi level, what it will be playing the role will be, it will be occupying such a position that the charge becomes minimum. That is the whole trick. Okay? So, if Ef is equal to E naught, net charge at the surface is 0, surface is neutral. So, with that background about the surface states or interface states, both are same, okay, we will move on to analyzing the Schottky barrier. This is the new diagram, okay, fresh appearance for this metal semiconductor contact. This was the situation right in the first lecture on the metal semiconductor contacts we saw. As we keep on reducing thickness of the delta, ultimately we saw this or this. So, we have put back the delta there. Metal, that thin delta layer of insulator which is always present, you can't make it 0. This is the depletion layer, QD, charge in the depletion layer plus, and this is the neutral region. This is the conduction band. After all, if this layer were not present also, you would have got that transfer of electrons, because phi m is larger than phi s we are talking of, electrons would have transferred from here to here. So, you got a depletion layer here. You got the depletion layer here and you get this entire band bending. Now, what difference is, in the absence of this delta and in the absence of interface states, you have to deal with only two charges. Charge in the semiconductor, depletion layer charge QD, which is actually equal to the charge within the depletion layer, okay, doping concentration into depletion layer width into Q. Okay, that is the charge that is present there. But in this situation, just notice what has happened. I have drawn the diagram. After all this band bending, suppose the neutral level is here. I just drawn that hypothetically. E naught I put there, phi naught at this point. Okay. There is a gap and I have just put light shading there in this portion. So, now let us take a look at it. Identify all the things. There is plus charge here, minus charge here, and that is why the conduction band or the vacuum level. If I call it as vacuum level, if I do not take delta as just vacuum itself, then also I can put the diagram, a gap delta. So, that is field is in that direction from right to left. So, the conduction band will be sloping up like that. Whenever plus is up, energy band diagram will dip down. So, that is there, constant electric field. So, slope is linear for that. So, that is the 0 level. So, from here to here you have got phi m. I am just going slow because you identify each one of those terms there. And when the band bending is there, if this layer is very thin, there can be tunneling. So, the actual barrier height is actually this one, this point, that is the phi bn. If delta becomes equal to 0, then the whole thing merges. So, that is the phi bn. If delta is small, the electrons do not care, they can tunnel through that, 10 angstroms hardly it matters. So, it is of that order that we are talking of. Okay. So, it can tunnel. So, that is the phi bn. Now, you see, because of this field across this oxide, there is a voltage drop, and that voltage drop is given by Vi, V interfacial drop. Okay. And this is the vacuum level will change exactly the same way as the your potential changes. I have not shown the vacuum level beyond this point. So, it comes down like this. So, between this point and this point the difference is chi. Okay, the difference is chi, that is between the vacuum level and the conduction band edge. So, what we have to see is what is the value of phi b n in the absence of the voltage drop in that layer. What was the phi b n? Phi b n was phi m minus chi. Now, the difference between the old theory and now present theory is that phi b n is actually equal to phi b m minus chi minus that extra drop that is present. So, you can see that there. Okay, see that drop V I. So, phi m minus V I minus chi leads to this phi b n. So, if you want phi b n, that is all. All that you have to find out is what is the drop subtracted from chi. It may be plus or minus. The way I have drawn, I have put it like that. Now, how to find out this V I? You find out what is the charge within this side. Okay. Q is equal to C into V, simple law of high school. Charge is equal to capacitance is voltage. So, voltage difference is charge at one plate divided by capacitance between the two plates. So, I can find out this drop V I as charge that is present on this side of this oxide or dielectric divided by capacitance of that layer. And what is the charge? Initially, if there is no interface state density, charge is only due to QD, depletion layer. Now, there will be charge corresponding to the interface state. Now, let us see here that this derivation is straightforward and simple. I have put the E naught here. This whatever we derive holds good for wherever that E naught is. So, this is for convenience I put it here somewhere. Actually, we have seen that it is about that difference phi naught is E g by 3 for gallium arsenide. So, if it is here and if the Fermi level is occupying this position now as it is drawn, what is the charge in the interface state density? So, Q is equal to Q I T plus Q D, that is the Q silicon. In the silicon, that is the Q. So, V I is Q divided by C I, that is all. If I find that, I am in business. Phi b n is equal to phi m minus chi is the original value. I have additional drop V I. So, I have to determine this V I, that is all what I have to do. Okay. So, now what is Q I T? What is Q I T? It is related to DIT. What we have assumed is DIT is there uniformly from across the band gap with the density DIT per centimeter square per electron volt. Now, how much is the charge depends upon whether it is acceptor or donor. The way we have put it here, this is the neutral level, Fermi level is above that. Please remember, this holds good if it is up or down. Now, if it is here, what is the charge here? Charge is DIT is the density per centimeter square per electron volt multiplied by the energy difference. The levels below the Fermi level are occupied. Okay. The levels above the Fermi level are not occupied. E naught, above E naught all are acceptors, below E naught all are donors. Fermi level is E naught. So, what will you say about the charges below E naught now? I repeat, below E naught all are donors and Fermi level is above E naught. That means, all the donor levels are below the Fermi level. that means all the donor levels are occupied, that means the charge in the donor levels is 0. Above E naught, all the levels are acceptors, and from here up to that point, part of them between E f and E naught are those acceptors at with DIT number per electron volt. They are acceptors which are occupied, and when they are occupied they are negative. When they are not occupied they are neutral. Okay? They are negative. Okay? Acceptor level is occupied with electron, that is the hole has been evolved into the valence band. So, neutral. So, how much is the charge? DIT is per centimeter square per electron volt. You have to multiply it by difference between E f and E naught. If I multiply, see the difference between these two levels is E f minus E naught. That multiplied by DIT gives me total number of dangling bonds, total number of states, multiplied by Q. Is it plus Q or minus Q? It is minus Q because these are acceptors. So, this is that. That is it. Now, you are in business. So, all that you have to do is use this equation, use this QD, which you know once you know depletion layer width. QD is actually equal to how much? Q, that is plus ND into WD, where WD is the depletion layer width, and QIT you know how to find out. Okay. Now, let us go back to this equation and see. So, with those things, now all that you do is just a bit of mathematical theory to evaluate that VI. So, that is what I have written here. Phi Bn is that, I can quickly go through. Vi is Qd plus Qit by Ci, total charge, and Qit I put as minus Q, because I did not have place to put that Q as Q on the other side. So, Qit is minus Qdit Ef minus E naught, and that term within the bracket Ef minus E naught I can put it as Eg minus Q phi Bn minus phi naught. See that this particular term is Ef minus E naught. You can go back and see. What you are writing is this, that is we are rewriting it as Ef minus E naught, I am rewriting it as total Eg minus this phi naught minus phi Bn. This portion is, okay, I think it is clear enough there. Yeah. This portion is Eg minus phi Bn minus phi naught. Subtract this phi Bn and phi naught from Eg, you get that quantity. That is what is put there. So, this is this second equation. Qd is of course charge per centimeter square in the depletion layer, which we have put down there. Now, Ci is the capacitance of interface layer, epsilon r into epsilon 0 divided by delta. Delta is the thickness per unit area, all these are per unit area. So, this is the capacitance. So, now you have got 1, 2 and 3. All that you do is put those things together, that is you substitute for this Vi. Okay. So, you will have here phi m minus chi minus Qd by Ci minus this quantity by Ci. That is what is put there. Phi m minus chi plus Qdit, because minus minus cancels, plus Qdit Eg minus phi Bn minus phi naught minus Qd by Ci. Simple mathematics, just you put. Rearrange this. Okay, you do not have to, you can just sit down and see. You have got phi Bn here, you get this equation. That is what we are looking for. You have got phi m minus chi into gamma, where gamma is this quantity. Just the concept is simple, phi m minus chi minus Vi. Vi we have estimated and put it here. When you rearrange everything, you get this equation. You have got extra term gamma Qd by Ci. Okay. Now, gamma is this quantity Qdit in Ci, and when you substitute for Ci, you get this. Now, you can see if Dit is 0, what is gamma? If Dit is 0, You can just go through that derivation yourself now, because it is all straightforward. Concept is that Vi determination adding to that. So, dit equal to 0, you get gamma equal to 1 and you get phi m minus chi. If dit is equal to infinite, gamma equal to 0, and gamma equal to 0, phi b n becomes equal to E g minus E phi naught. So, infinite dit, the phi b n is independent of phi m, flat, that is flexibly cleaved surface. In fact, dit equal to 0, gamma becomes equal to 1, ideal case phi m minus chi, that is what I have put down here. Okay. So, this is the, so there are two limits, one is dit infinite, you get phi b n is equal to E g minus phi naught, that is Bardeen's limit. That is what Bardeen said, the whole thing is controlled by surface states. And Schottky limit, the guy Schottky, he said ideal surface phi m minus chi is the barrier height, phi b n, that is the Schottky limit. Every time it is within the two limits. Now, the impact of this we will see when you go on seeing. Now, you can see your life becomes horrible, because the phi b n now, what you think it is phi m, you choose large value, you get such a value. If dit is large, you are stuck with the phi b n equal to E g minus phi naught, and invariably you got large density of states, invariably you get E g minus phi naught as phi b n. You put aluminum, you get phi b n in gallium arsenide equal to 2/3 of E g, so it is quite high. You get gold, you get 2/3 of E g, high. You get rectifying contact, where you put gold, aluminum, everything. You thought aluminum phi m is very small, it will make ohmic, it is not going to make. How to sort it out, that sort of thing we will see next lecture. Okay. Next lecture we will see how to do this particular thing, and also IV characteristics. So, today we will close down with this particular thing.